Thank you for inviting me. I'm Dr. Vikas Malik. I work in Department of Physical Sciences, JP Institute of Information Technology, Noida. The topic of my talk is coarsening dynamics of the Coulomb glass model. So the Coulomb glass model is electrons localized on a lattice, which we are considering here. We are considering a 2D lattice, and the electrons are interacting while non-screen Coulombic interaction. In this talk, we'll basically be discussing how the dynamics of the uh, Coulomb glass model evolves with time, and we'll be looking at the growth laws, which are well known. So if we just look at the pictures first, these are the domain pictures at different disorders which we have considered. You can see the disorders considered are till 0.175 because if you look at this diagram here, this is the phase diagram for the 2D Coulomb glass model which we gave. And you can see that after 0.2 here, there is a paramagnetic phase. So all the W's are less than 0.2. We quench our system from a high temperature phase, paramagnetic phase, to our T is equal to Tc by 2. And this is the antiferromagnetic phase. These are the domain diagrams. So since the order parameter is staggered magnetization, we look at the staggered spins. Sigma I is equal to, sigma ij will be equal to Sij minus 1 to the power I plus j. And the domains are basically sites which are connected to each other, which have the same staggered spins. So you can see that for W is equal to 0, where there is no disorder, the domains are quite large. This is at a particular time of 10 to the power 3 Monte Carlo steps. We are doing conserved. The number of electrons are conserved. We are working at half filling. So number of electrons is equal to number of holes. And you can see at 0 disorder, the domains are quite large. And as the disorder is increasing, the domain size is quite small. We can look at the correlation function, and the correlation function very nicely scales with the correlation length. So you can see that at different times for a particular disorder, the correlation length, correlation function scales very nicely, and also at the different disorders. Not only that, it also follows this Ujike function, which is actually the fitting form for a nearest neighbor or a short range interaction. This is the correlation length versus time. So you can again see that at W is equal to 0, we are having a T half law. And as we are increasing the disorder, the correlation length is decreasing, the growth is slowing down. A little bit of theory. So the dynamics is controlled by this equation. This is a well-known equation. A is your diffusion constant, and we are basically looking at activated type of dynamics. This is your barrier energies. So if your barrier energies are constant, are 0, then you have your famous LCA law where L will scale like T half. If you have barrier energies like this, then you again have a power law, but with a modified exponent Z bar, where Z bar will be having value 2 plus W by T. This was done quite a long time back. And finally, if your barriers are going like, if your barrier energies are a function of L, if EB is L to the power 5, then the growth law is the logarithmic growth law. And in the work on 2D RFIM by Corbett et al., they showed that there is a crossover from this power law, T1 by Z, to basically this logarithmic growth. So similar results have been obtained here. Z effective is basically Z bar. So you can see that, for example, that this W is equal to 0.125. This is almost straight. This is Z bar. And then when it starts to increase, basically there is a crossover to the logarithmic law. Z bar also follows this nice linear fitting, 2 plus W by T as before. But the difference comes that when we fit it, then our value of phi is something like 1.5. And when they saw it in 2D RFIM, it was basically 2. So there is a difference. Now, the difference could be because of two things. One thing is this phase diagram itself. It's well known that for 2D RFIM, there is no phase diagram. If we are working at T is equal to 0 and we keep on decreasing a disorder, there is no antiferromagnetic phase, there is no ferromagnetic phase. But we have shown that for a Coulomb glass model, there is actually a transition from a paramagnetic phase to an antiferromagnetic phase. So the difference in the value of the constants which you have achieved could be either due to the fact that these are size effects, the way we have written, or it could be because the equilibrium properties are actually different. The ground states are very different. Taking this forward, we then looked at another system, similar system, but which we call asymmetric Coulomb glass model, in which the number of electrons, let us say, is a little bit more than number of holes. So rather than having k is equal to half, we had k is equal to 0.475 or k is equal to 0.55. Again, you see that there is a difference in the ground state, and we thought that this will create a difference also in the dynamics. These are the results for k is equal to 0.45, but you can see that the growth is pretty nice, just like in the k is equal to half, the half filling case. Correlation function also scaled pretty nicely again. There was no problem with that. If we now look at the correlation lengths, this is for the CG model and this is for the antiferromagnetic case. You can see there is a slight slowing down. This theta effective is just your Z effective, Z bar actually. And there is a little bit of difference between k half value and when you are away from the half filling factor. Now, the next thing which we did was, we took up a square domain and we tried to basically shrink this. Now, this is a famous paper by Shore et al., in which he actually used this simulation to show that you can actually predict the correct growth laws by just finding out the time it needs to shrink a square domain for 2D and a cubic domain for 3D. He actually proved for the 3D domain that the growth law is logarithmic for competing interactions. In our case, when we did this, this did not lead to any tangible results. The results were actually not at all, pretty confusing to say the least. But it did lead to something of the understanding of the physics, that if, for example, if you just take a square domain like this and you put an extra electron here, then the way the domain basically goes, is destroyed, is that this spin, if you look and just think about globular dynamics, this has zero energy. And if you flip it, it doesn't require any energy. And basically the domain starts to flip from here, and then when it will come here, this spin would like this not to be of the different sign. So this will create an energy barrier. So what we basically concluded in the end was that it is possible that there is a slowing down. We are seeing a slowing down, but we are not seeing any logarithmic law which is seen in the experiments. The reason could be that we don't have a very large system. For this sort of an effect to take place, you need a very large domain, and obviously then only this these extra spins will be able to create a problem. So more the number of, larger the domain, larger the number of extra spins this domain shrinking will encounter, and that means that the barrier energy will scale like L, and you should get logarithmic law. So experiments show logarithmic law. The theory which we gave, or the argument which we gave, predicts that we should be able to see this logarithmic law, but for our system, we were not able to observe it, and we were not able to actually observe it. So this was finally just left as an open question, that will we be able to observe this if we were able to increase the system size. So one has to basically understand that if a 512 square simulation takes 10 days, if I double the system size, then it would take me many months. So that's the problem. Thank you.
Thank you for the interesting talk, questions.